we can move to the next presentation. As you already introduced by Jan, that is probably the first direct use of this database collection.
On peut utiliser la souris. Okay. Well, good morning. So, as Kevin introduced, I was checking the numbers or putting some numbers on all these nice traps all over Europe. And we had several rounds of estimations because there was quite a lot of diversity in the data when the database was elaborated. So I just showed this general picture from the sedimentary basin of Europe, and as Kerry said, we're focusing on traps because of a closure. We want to inject hydrogen, but we also want to recover it. So we are really looking for traps where we could have, of course, a porous media, but also a caprock, and where there is a closure so that the hydrogen doesn't leak out, or we could recover most of it. And given the specificity of the traps, you can have different settings, as shown also by Kerry, depending on the geological configuration of the different traps. It could be anticlines. I don't know if this works. Okay, I will do without a pointer. We can have anticlines, stratigraphic traps that could be used to store hydrogen. Then the question is, how deep do we want to go, or how shallow do we want to look for traps? And in the project, we set some limits. Sometimes we exceeded them later on, but that's we try to focus on something that seems reasonable in the order of 500 or 400 meter depth at the minimum. So in the database, there was quite a lot of traps. This is a view of all the traps that were identified in the different sedimentary basin. And I will stress again that because there is nothing, it doesn't mean that there is no trap. It's just a matter of availability of the data, particularly for aquifers, because they don't have such economic interest, so sometimes they are not explored for any reason. The different traps have been used in different ways in the past. They could be used currently as underground gas storage. So we could imagine that those could be converted right away to hydrogen storage. Some of these traps were oil and gas fields that could be converted back to hydrogen storage, given the right conditions, of course. And there are the deep saline formations that are spread all over Europe, much less characterized, potentially quite large, but sometimes the traps are missing, or the identification of the traps are missing. So given the diversity of porous structure and use, we could face different technical issues. If there are wells, the issue would be the integrity of the wells with respect to hydrogen. If there are hydrocarbons, the issue will be the mixing of hydrogen with the hydrocarbons and of course the recovery of it. And of course in all the storage, the question will be the caprock tightness for hydrogen, and eventually any reactivity that will occur. So the different traps have also different maturity level. Basically, the underground gas storage could be, almost readily converted to hydrogen storage. Depleted hydrocarbons could be next in line, and deep saline formation, because of characterization problem, will come probably later in terms of maturity. So for all of these traps, there are a lot of uncertainties. Unless you are focusing on a particular trap. But our work was really to carry out the estimation at the European scale. We decided to make synthetic model for each trap, so that we could estimate the capacity for each of the more than 1,000 traps in the database. So we estimated this in terms of volumetrics, as long as there were information available on basics of the traps, such as the area, the depth, the thickness, porosity, and so on. That already eliminate quite a large number of the traps that were identified in the database. So the simplified model is really a cartoon of what the reality will look like. But we could, based on the information of porosity and permeability, on porosity mainly, thickness and so on, we could estimate what is the porous volume, that is the volume available for storage. And from there, once we know the porous volume, we could estimate what could be the capacity, the total capacity of hydrogen storage. Correcting the porous volume by two factors. One is easy, it's the influence of pressure, temperature on the hydrogen porosity, and this is the volume factor B. The other one is a bit more tricky, it's the efficiency of hydrogen storage. It will depend on the type of storage. So this volumetric estimates will consider different efficiency for the different storage. One for hydrocarbon based on the oil and gas recovery factor. One for hydrogen gas or for underground gas storage based on the working gas and total gas ratio. And the other one for deep saline formation, where there is basically no commercial operation, and we will be using an analog to CO2 storage efficiency. This storage efficiency for CO2 was developed about a decade ago and was analyzed later by IEA. And this analytical approach fits fairly reasonably with the DOE database on CO2 storage. It's based on the assumption of efficiency of replacement of the in-situ fluid by, in this case, CO2, but also by hydrogen, when changing the properties of CO2 by properties of hydrogen. And comparing that with CO2 efficiency from the DOE database, the hydrogen efficiency is about 1/10 to 1/30 of the CO2 efficiencies. But of course, this is quite a crude approximation of this efficiency ratio. So how good is this estimate? So we compare this volumetric estimate to published data. And you see that we had estimates based on the uncertainties. We had a quite large range of capacity between the 1U and 3U for aquifers, referring to the SPE management system. And our mean estimates in green falls fairly close to dynamic estimates that were published in 2020 by Meripass. Another example, still from Meripass, that was the only available dynamic capacity estimated at the time, and we were also very close for this second aquifer. So that gave us confidence to perform or to expand this approach to the different traps in the database. And here is a view of the database or the capacity of the different traps throughout Europe. You have the 800 points onshore, offshore, and a bit less on the onshore. And we see here that the spread of the different type of porous trap is different from country to country due to data availability, and also the size of the potential or the capacity is very different from country to country. When you look, for example, around the North Sea or in Southern Europe, you have different storage capacity as expected. So then we could compile this information for all the countries and classify them in terms of capacity, basically underground gas storage converted to hydrogen storage, contingent resource, oil and gas fields, and prospective resource, which will be the deep solar informations. And for each countries, we estimated the mean and some kind of uncertainty range for the different capacity of the country. Well, this is available in the report of Work Package 2 on the iStory's website. So that gave a compilation for the different countries. We have pie charts corresponding to the different storage capacity, green for oil fields, dark blue for gas field, light blue for saline formations, and gray for the underground gas storage. So all in all, we have quite large number of energy storage capacities. And not surprisingly, the deep saline formation is quite small because there is quite a very small number of traps that were identified. When focusing on the onshore, we have still quite large numbers. But the question then is this relevant, or is this too much or too little? So jumping ahead to Work Package 5 results, there were some scenarios of storage demands that will be presented tomorrow, where porous media were identified as a storage as a storage potential for hydrogen. And then in Work Package 5, they could identify the requirements that are the squares in this graph. And we compare that to the capacity we estimated in the different countries, that's the color dots, and compare that as well with the published data from the hydrogen backbone report. So for most countries, there's probably enough storage capacity for hydrogen, except maybe for Italy, where we see that what we estimated is a bit below what is required, but that's probably due to the data availability, which is not, which was not quite large at the time of the work. And for some countries, there is no information because of lack of storage, for example, in Sweden. But for other countries in Work Package 5, there was no requirement for porous media, for example, for UK. So then the question is, these big numbers, are they within the ballpark of what is required? So we selected 22 traps throughout Europe, trying to locate them or pick them close to the proposed hydrogen backbone. So they are spread all over Europe, and we wanted to combine both depleted gas field, underground gas storage, and aquifers when possible. So for these 22 traps, we model, we try to estimate the dynamic capacity based on this synthetic model, assuming a development plan and assuming that they were all have to be developed the same way. And we compare the dynamic capacity, this is a vertical axis on this graph, and the static capacities. Ideally, we should be on the diagonal, but we see that we have some discrepancies, of course, even with these synthetic models. The dynamic capacity differs sometimes quite significantly from the static estimates, and that is, of course, expected due to the approach. And then we looked at how long it takes for the hydrogen bubble to stabilize in the system, both for the aquifers and depleted gas fields. And we see that for most of the most of the case, about 4 or 5 cycles, it's fairly stabilized. But in some of these gas fields, it takes almost 10 cycles for the working gas to stabilize due to the exchanges between the hydrogen and what is left in terms of gas. This approach has a lot of uncertainties, as you can imagine, and you should not rely on that for site developments. The approach is at the European scale, quite schematic, but it gives us an estimate of the availability of storage resource throughout Europe. In this approach, we estimated mostly the total gas, and we have seen that the cushion gas could be significantly different. When we looked at underground gas storage and depleted gas field, without any commercial consideration or strategic consideration, there is enough room. Of course, in real life, there will be some other constraint, and they may not be available on time or when required by for hydrogen storage. The capacities are available in most countries. However, we didn't consider any commercial aspect or market aspect or commercial or country requirements such as security, strategy, and so on. And most of this storage for hydrogen will take some time, except maybe for underground gas storage. So there might be some issue of time to market for some of these traps, especially for aquifers, since we need to further characterize them. And with that, I'll take any question you wish to ask.
We have 15 minutes for questions. We need questions.
15 minutes.
So another question from the chat. So from Jonathan, the storage of hydrogen in deep saline formations obviously requires structures to trap it, unlike CO2. So how is the storage efficiency of CO2 storage comparable to hydrogen storage? For a steeply dipping structure, can you use a lot of the capacity for hydrogen storage?
Well, the efficiency factor, of course, is a way to avoid any direct numerical simulation. At this scale, we could not afford to carry out numerical simulation for each of the storage. However, using this efficiency factor give us an estimate of the capacity of the hydrogen storage, which in that case will be very similar to CO2 storage, changing, of course, the properties of the fluid. This efficiency factor doesn't take into account any cycling at all. So when you consider CO2 storage, you inject CO2 and let it there. That gives you the capacity. And the capacity we computed for hydrogen storage is, let's say, the first filling of the storage, of the hydrogen storage. So that's a first approximation approach to capacity estimates.
Another question?
Thanks, Jan. I wanted to ask, what do you see as the next steps to improve our understanding for hydrogen capacity? Do you think we need real field data, or do you think we need to develop better models?
Well, the models I built was really synthetic, so it doesn't take into account any structural effects at all. So this is one crude approximation. It's better than a parallelepiped, but it's still an ellipsoid, so it's not perfect yet. So if you want really a capacity for a given site, I mean, you have to develop your site-specific model. So the next step may be to avoid this efficiency factor. It's do an atlas like the CO2 atlas in the US, where they perform quite a large series of numerical simulation. But I still doubt they use the real structural model. So it's probably better to do numerical simulation for all of these traps, trying to get statistics out of it. But there will be some bias anyway. High stories too, we could try to do that. It would be fun.
Okay, yeah, I have a question. Yannick Pesson from IFP Énergie Nouvelle. Thank you first, Yann, for this very clear presentation. If I understood you well at your conclusion, do you suggest that the first capacity would be the conversion of existing gas storage capacity? I am correct?
Yes, this is what I think are the most ready structures. There will be some work needed for that, of course. I mean, it's not... You need to make sure that your storage could be operating properly under these circumstances. The next in line will be the depleted gas field. Because in terms of cap rocks, they are probably very efficient. The problem is that they may be too large and they may be offshore, so that's a bit difficult.
Jan, I just opened the report about CO2 storage capacity from UGEA capacity. It was 2009 maybe, just in the internet. So the conclusions of UGEA capacity, first pan-European project in CO2 storage, UTOPAT, was that in the oil and gas fields, capacity is smaller and small, but a lot of data. In aquifers, much larger capacity, but less data. And also we know all over the world that capacity for CO2 storage 10 times higher than in depleted fields, in hydrocarbon fields. Why we got opposite results? Can you explain us?
Yes.
For hydrogen, opposite results for hydrogen. That was for CO2 storage.
Yes, I can explain, of course. For CO2 storage, we are looking at anything that could be used to store as long as there is a cap rock. Here we are looking at traps, so we need closure, and particularly for aquifers. And as Kerry said, there's quite a gap of data in terms of identified trap in aquifers. So there is probably much larger capacity in aquifers than what is shown here. But the problem is the traps were not identified, so that explains the large discrepancies, I could say.
So is a conclusion that if we have more data, more physical data, etc., then of course we will have larger capacity.
If we have more data on traps, I mean that's exactly what Kerry said. So I'm
more geological, geophysical, then we will get.
Yeah, if we have more data acquired, more interpretation for aquifers, we very likely will have much more capacity. But so far they don't have any commercial interest, so we have to convince someone to pay for that.
Thank you, Jan, for the question. Maybe a last question from the online audience. We have to give them the mic too.
Yeah, so how much is the dynamic capacity typically reduced from the preliminary static estimated capacity? And the comment going with this is, I assume this is site specific, but is there any rule of thumb for this?
Well, I was expecting to find a 1-to-1 ratio, but on the 22 sites we picked, the dynamic capacity, even with this synthetic model, for some cases was larger than the static, and for other cases was smaller. So there is unfortunately no rule of thumb.
And the last question from the in-person audience.
Pedro Pereira from University of Évora. First of all, I would like to thank you, your great presentation. And I would just like to make a comment on that, the storage capacity, the potential, because the synthetic case that you showed is like a typical anticlinal structure, like a structural trap, but we don't know what are the stratigraphic traps, for instance. So maybe the potential could be much more bigger than the known that we know from the project results. So, but for that, we need a lot of geophysical data, even wells, and try to characterize, especially the saline aquifers, because for sure they have a great potential. So, thank you.
Well, I agree. I mean, I can only agree. But when I was asked to estimate the capacity at European level, given the data available, I even had the difficulties finding porosity, permeability, well, not even permeability, porosity, thickness, net thickness, area, and there were quite a lot of discrepancies already at this basic level. So stratigraphic traps was an approximation. Another one.
Thank you, Jan, and thank you all for the questions. It's now time for our first break.